Good afternoon. Welcome to lectures 85 and 86 for the course Thermodynamics of Materials. Today we will continue with solution thermodynamics. Okay. So today we will actually give you the summary. We give you the summary of last day's discussion because there are some audio disruption, sporadic though, audio disruption time to time. So we want to give you. I want to give you the summary of last day's discussion. Okay, so that we uh, revise the whole thing. We will go through this once more. Okay, but the short form of this of the salient points. So this is, and I hope today the disruption, noise problem, audio problem won't be there because we have changed this microphone, and so you hope actually today there won't be audio problem, and other things will also improve. Let us see. But start summary. Summary of the discussion of the discussion on mixing functions. On mixing functions in the last class. Okay. In the last class, that is lecture 83, 84. Lecture 83 to 84. Just including some missed out points, some missed out points. So this is today's job. Just reviewing last day's class, a quick review. The first is, you recall what I wrote, Na moles of A, the mixing process, Na moles of A pure plus Nb moles of B pure is undergoing a mixing process under constant pressure, constant temperature, and the process is mixing. What results? Na plus Nb moles of AB solution. This is the process. Okay, recall this. This is actually unmixed state. This is unmixed state. You may call state 1, you call state 1, and this is the mixed state. Solution means mixture. So mixed state, call it state 2, state 1, state 2. Now start. What we see? Delta G system, the results, instead of explaining everything, I am giving you the results. So delta G system, in short I am writing system 1 to 2, the process is 1 to 2, is G2 minus G1 is actually what I wrote, delta G prime, remember, PT delta G, delta G M prime for extensive property, M for mixing, constant pressure, constant temperature, all given. Okay, is what? You tell me what? G2 Na G2. What is G2? Na moles of, but free energy is now partial. Na bar not pure, impure. Na bar. Likewise, Nb Gb bar. This is G2 minus G1. Minus G1 is what? Minus G1 is what? You see, unmixed state, pure state, the standard state. So you can write similarly Na Ga0 plus Nb Gb0. Recall this. So you can add another line, Na Ga bar minus Na in common, Ga bar minus Ga0 plus Nb in common, Gb bar minus Gb0 is what? You recall, this is actually, this is called Ga bar M. Ga bar M. So Na Ga bar M plus Nb Gb bar M. Let us give the name of this. This name is what? Tell me. Integral total, as different from molar. Total means total for Na plus Nb moles. Molar means for 1 mole. One is extensive, total is extensive, molar is intensive. Integral total free energy of mixing for Na plus Nb moles of solution. Moles of solution. Total free energy integral total free energy mixing for Na plus N moles from, what is this property? As you know, extensive property. Property. This extensive property and intensive property you studied at the beginning, introductory terminology of thermodynamics, and they are used at the concluding stage of our study of this course. So you see, so this is very consistent subject and is okay. What is and this is actually, the concepts are useful from all through the course. Okay. So you cannot avoid any concept. This is what Ga bar M is partial molar free energy of mixing of A. What is this? This is likewise GB bar M is partial molar free energy of mixing will be right. Free energy of mixing of B. This much, okay, delta G system, this much, okay, partial molar is what? Write this, keep on writing. This is what Na, Ga bar M or Ga bar minus Ga is RT ln activity of A plus Nb times RT ln activity of B. So you can take RT common, Na ln A plus Nb ln AB. Call this equation 2 and call this equation first one, the top one, the process, mixing process, as equation 1, 2 so far. So now actually what we will do this now, delta, this is delta, see, delta Gm Pt. This is not unprimed, so should be intensive property what it is for 1 mole. So you divide by Na plus Nb, so you will get the result for 1 mole. So delta Gm prime Pt by Na plus Nb for 1 mole. So write this right here. This is integral means when the combination of the two is the integral, and partial is alone, A alone, B alone in the solution. In the solutions, so partial, we use the term in solution, partial pressure for gas when there are number of components. So partial. So delta GPT would be what? Integral, still integral, but no more total. It is for molar, because 1 for 1 mole, molar. This for Na plus and molar, right? This molar free energy of mixing. I am just saving space. Free energy of mixing free energy of mixing of actually mixing of free energy mixing for 1 mole. Molar obviously for 1 mole of solution. For 1 mole of solution. Molar means 1 mole, so you can still write for 1 mole. This is Na plus Nb moles. This is for 1 mole of solution. What is the property? Intensive property. Property. What it will be? Just divide this by this. This actually you can see here. It is actually, if you look at this, Na, if I pick up from this, pick up from this point, Na by divided by Na plus Nb, both sides, Na plus Nb times Ga bar M plus Nb divided by Na plus Nb Gb bar M. Now what is this? What is this? This is called XA, mole fraction of A, and this is called mole fraction of B. So write this accordingly. XA GA bar M plus XB GB bar M. Okay, right. Keep on writing. Is XA GA bar M plus XB GB bar XA GA bar M plus XB GB bar M. What it is? Tell me. Keep on writing. Is XA, as you know, GA bar M is RT ln A, RT ln A plus XP RT ln activity of B. Now RT in common, XA ln A plus RT in common, sorry, RT in common, yes, right, plus XB ln AB. Okay. Now this is actually, we have a list of, this is actually called, this equation is is okay. Equation 3. So one original, the process of mixing 1, 2, 3. Now in a solution, a activity, you know, in a solution, activity of A is less than 1 and activity of B is also less than 1, and log of less than 1 is negative. So hence from 2 we get from 3. Okay. Hence, oh, hence from 2 or 3 you can consider either, but it is better we consider from 2 will be better. Okay, since actually we have already, so it's okay. Okay, so hence from 2 means this one, follow this means this, means this, 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 this. So hence from 2 we get, what do we get? Let us write delta G system. Acha, here delta G system 1 to 2, you can write under constant temperature pressure, delta G system 1 to 2, that is better right here, here. This is constant temperature, constant pressure process, so constant T, constant P, just additionally right here. Okay. So I write that, delta G system 1 to 2 under constant P, constant T is what? Right? Delta Gm prime Pt is what? This one. Since activity of A is less than 1 and activity of B is less than 1. So log of less than 1 is negative quantity in either term. So what you will have, this is a negative quantity. It is a is negative, and our criterion, we know the criterion is delta GPT is negative, means it is a spontaneous process. This also I will, well, let me write this. Okay, hence mixing is a spontaneous process. process. Okay. He note here more discussion about this criteria, whether this criteria or any other criteria like delta G negative or delta S universe positive, etc., etc. This will be discussed a little later. Okay, before that I have to finish some other things, ideal solution properties. Let me. But I mentioned here more discussion on criteria of spontaneity, on criteria of spontaneity of spontaneity spontaneity a little later, a little later, a little later. Until then, we will consider other issues like say ideal solution properties. So this is so we will consider this. Shall I now? I will actually note equation 2, equation 2 out of 3. Okay, I am just removing this part. Hmm. This was I am completing this. Equation 2 is about delta GMPT. This actually I have forgotten this. Delta Gm prime Pt. This is equation 2. So we continue from note equation 2 or equation 3. Equation 3. Note equation 2 or equation 3 is applicable to any binary solution. Any binary solution, ideal or non-ideal. Ideal or non-ideal. Non-ideal. That is real solution. The solution showing deviation from ideality, that is positive deviation or negative deviation or ideal. Consider the case of ideal solution. Let us consider the case of ideal solution, which is a good reference, which is a good reference for which you know what will be, what change you will make here. Remember, this is activity of for which ideal solution means activity is Raoult's law. Activity of A is what happens here? is XA and activity of B is XP. So let us put in these things. So, so from 3, now we consider this. Because equation 2 or equation 3 is applicable. So from 3, because we will be interested in integral molar rather than integral total. Integral molar rather than integral total. So we will be considering 3. So from equation 3, so from equation 3, if we substitute this, we get what? Delta Gm, sorry, what happens? Delta Gm 3, if follow 3 is this, delta Gm Pt, but since it is an ideal solution, so we add a superscript id for ideal, and other things are same. Pt is what? What will write? RT XA ln A means XA, ln XA plus XP ln AB, XP ln AB means XP. This is one important property of ideal solution. Okay, call this, box this to show its importance, to highlight this and give an equation number sequentially 4. This is okay from equation 3. So next is what? Now I don't think I need all these things are anymore. Okay, so delta GMPT is what? This equation 3 will be retained. Equation 3 will be, since I will consider integral molar only, so this is no longer required. Remove this, and about this you need only the result. So remove this, the last line, rather equation 3 only retain. Equation 3 you retain this, and these are all discussed. Just write this as delta GMPT. This may be useful. So you may refer back to this. Okay. So you have seen this mixing is a spontaneous process. We have already seen. Okay, let us keep on writing from considering the next property. So next, what is this? Delta SM ideal PT. Acha, what's the name of this? What's the name? You remember the name of this, and then similarly name. What is the name of this? Integral. This is what? Molar. Integral molar. Integral molar. Acha, right here somewhere. ID I have written ID superscript ID denotes ideal solution. Ideal. Okay, ID for ideal solution. This ID means for ideal solution. Similarly, integral molar, tell me this integral molar entropy. This is integral molar free energy of mixing. Integral molar entropy of mixing. Now how will you get delta SM? There is a standard technique to get entropy from free energy. What is this? Derivative. Take the derivative with respect to temperature. So you just write this minus del T temperature derivative of delta Gm ideal Pt, just complete everything under constant pressure and composition. What it result? I'll explain this part. Okay, I have some comments to make here. Acha, how do you get this? Acha, let me write this. What is this? You take a ddt. Del dt composition is fixed. Xa, xb don't change, and temperature pressure okay is not involved here. So it is minus r, right? This xa ln xa plus xp ln xp. Happy? Okay. This is box this. This is another important property we found just now. It's called equation 5. Acha, recall, first of all I tell you here, this is, this note this, this is positive. Why positive? Why this is positive? Because again xa is less than 1. Mole fraction in a solution is less than 1 and xb also less than 1 and log is there. So ln xa is negative, ln xb is negative, so negative and negative positive. So positive since xa less than 1, xb less than 1. Okay, this. Recall why, from which relation you get this basic relation. So let me write here. Recall, just let me write here. Acha, here. How explanation? Some explanation. Delta Gm3 is necessary, no? Delta Gm is necessary. So let me write somewhere in short. This is equation 3. I have to write something now. Okay, so equation 3 I am writing somewhere. Okay, I am just removing this summary. We will know this summary is just, I am saving equation 3 here to save okay some space. Okay, equation 3 is what? Delta Gm. This I will use later. So I am writing delta Gm id pt delta Gm. Okay, delta Gm id pt is where? Okay, no, I am sorry, this is not required anymore. Okay, so no, let's remove this. Not required anymore. Okay, because we are considering ideal solution. So underline where? Consider the case of ideal solution. So all ideal. Also ideal is given in the superscript. Ideal molar entropy of mixing. Then what shall I consider? Okay. Explanation. Little bit explanation here. Little bit explanation. Follow this. Recall. dg is vdp minus sdt. Recall this. dg is vdp minus sdt. Okay. So this is actually valid for valid for fixed mass, fixed composition system. Example, e.g. 1 mole of an ideal gas, 3 moles of an ideal gas, 4 moles of iron, 5 moles of oxygen, 6 moles of water, e.g. 1 mole of an ideal gas. This is well known to us. From this you can write, or this is the general procedure or technique, and and d delta g will be what? D delta g would be what? This delta will apply here. G will be delta and S will be delta. What it is then? Delta V dP minus delta S dt. Okay. Now this is actually okay. Now here, what is the delta G? I will actually give some comments, explanation, discussions. Okay, so that you will understand this delta G. Acha. Here I am writing. Here, let's have some space. Here, delta G applies to a first one is fixed mass, fixed composition. Second one, no, second one is for variable mass with or without variable composition, as I told before, like chemical reaction system, like solution system. So you careful. So delta here, delta G applies to a variable mass with or without with or without with or without with or without variable composition. Variable composition, e.g. chemical reaction system, e.g. one chemical reaction system, chemical reaction system, two solution system. Solutions system. Solution system. Happening for chemical reaction, for chemical reactions system, for chemical reaction system, for chemical reaction system, delta G is G products minus G reactants minus G reactants, G products minus G reactants at any given state, at any given state, at any given state, at any given state, not two states involved. Note, not two states involved. Note, not two states involved. Note, not two states involved. Okay. And for solution system and for solution system, For solution system, for chemical reaction system on a given state, as I have said, but for solution system, two states will be involved. So let us say for solution system, delta G is what? G2 minus G1, two states, 1 and 2. Two states, two states, 1 and 2 involved. Okay, happy? 1 and 2 involved. So from above we may write from here. So from above we may write, what we may write? From okay, we may write d here from this t, rather the del t of delta G under constant pressure, means this will drop away, this term, first term. So will be constant pressure, and also composition. I will explain this. Why composition is what? Minus delta S. Right, okay. So this is actually, this we have used here. This is the rationale of writing this here, this one. Coming from here to here, and this actually we have used. Okay, very good. Minus delta S. Now pressure is very easy to follow, because if pressure constant, then only delta G is a function of temperature, and we have got the derivative. So pressure is constant, but composition is what? About composition. Note the significance of this derivative. Try to understand this derivative. Note the significance of this derivative. Note the significance of this derivative. What it is done? See, delta G is I tell you what delta G. Okay, here is okay. It's okay. Delta G is measured. The significance of this derivative. Delta G is found out is found out from a number of experimental runs. From a number of experimental runs. Number of experimental runs with varying t. With varying t, because t is a variation, but without varying pressure and composition. This is actually, you have to note, that is, but without changing pressure without changing pressure. How is the font size? You can read this. Yes. Okay. Okay. Thank you. Okay. Okay. Thank you. So without changing P, so what you will do? Keep your number of runs. What you will do? Keep P at the same value for each run. Keep the keep P at the same value, like say 1 atmosphere, 1 atmosphere in each case, or 2 atmosphere in each case. So, so pressure is constant, but pressure is vary. Is constant for each run, but this constant value is changing. I'm sorry. Temperature. In case of temperature, temperature is a constant pressure, constant temperature process. But how temperature can vary? How do you consider? We consider that delta G obtained for different temperature. Each time temperature is constant, and pressure of course constant, composition constant. Then when temperature varies means next run pressure composition as before, but temperature is another one. And under that constant temperature, result is obtained for delta G. And again T3, again delta G obtained. So you will get a number of delta G and number of T's, while pressure and composition remains there at their original value or initial value. Then this derivative will produce this negative of entropy change. This is the meaning. This we will often use. Why we say constant pressure, constant temperature, but again see derivative we are taking. The practical, okay, mathematically we can always do. Mathematically we have done also. But the meaning of this, we carry out a number of run, experimental run. Each time, each is under constant pressure temperature. But this constant temperature, say first experiment T1, pressure is P. Second experiment temperature is, this is constant pressure, constant temperature, and we get delta G value. Find out experimentally, or you can estimate also experimentally. Say. Then we consider next one is T2 temperature, and pressure is P. A composition of course the same. Then you carry out again, find out again delta G, or experimental find out. Then second delta G for second temperature, third delta G, fourth delta G. Take all these delta G's against temperature, and while P and composition remain same. So I am explaining this. Please follow me. Keep P at the same value for each run. For each run, and so what I have said, delta G is found out. Sorry, is found out. Sorry, found out from a number of experimental runs with varying T, but without changing P and without changing composition. This part I will take up. Without changing P and without changing composition. That is, P and composition are fixed. How to explain this? And okay, this one, what should I say? Here, let me see. And changing without changing composition. What does it mean? Without changing composition, that is keeping the that is that is, actually give a star here, and let us go to the top. Use this, that is keeping the same composition, that is keeping the same composition of product and reactant, okay, a product and reactant is this, product and reactant is this, of products and reactants of products and reactants for chemical reaction system, or chemical reaction system. Chemical reaction system considers product and reactant, as I have said somewhere, as a product and reactant. So the same composition of product and reactant, same composition. Okay, so if the reaction is A to B, say consider 60% A, 40% B. So keep this same composition. All cases, only temperature will change. Pressure will not change. Composition will not change. So keeping the same composition of product and reaction for chemical reaction system, but product and reactant we will not use. We will use the term and or keeping the for solution system, what we should write? Right, keeping the same composition of the solution system. So what happens? So this is actually I wanted to mean the significance of this. Okay, this is over. Huh? So very good. Now what I want to tell you in short, what is this? What is this derivative? And which produces minus delta S? And which has been used here? What is this? How to carry out this? What is the physical significance? Get delta G under constant pressure, constant composition, but different temperatures. How for a given run, temperature is fixed, pressure is fixed. Like this, temperature, pressure fixed. And composition is say you have considered 70% A, 30% B. So this fix that. To get this fixed pressure is say suppose say 2 atmosphere. Okay, well, commonly 1 atmosphere. Say 1 atmosphere. Fix that. Don't change. Temperature is first say 500 Kelvin. Then next is 700 Kelvin. Still next 900 Kelvin, and still next say 1000 Kelvin. So these 4 temperatures each time temperature pressure constant. Each time the process, and what is the objective? Get delta G, delta GM ideal. Get delta GM ideal each case. So you have 4 such delta GM ideal under constant pressure, constant temperature each time, but 4 different temperatures and against 4 different temperatures. So take a plot, make a plot. This delta G, rather here delta GM ideal versus temperature. Each time pressure, temperature constant, and composition also you have not changed because you consider 70-30, 70% A, 30% B, like this. Okay, or say 7 moles of A, 3 moles of B. That's nice, no problem. Same. Don't change. Change only temperature. Otherwise, same. Repeat. Then you will understand the significance of this. Very good. If this is okay, then let us move on to the next one. We are actually I will remove this since explanation is given. So I think you will not mind if I remove this. Okay. So I have already mentioned that delta SM ideal PT is positive. Note this. I have already okay explained this. So remove this. this explanation is removed. In fact, I can remove this also, remove this part also, but later on I will remove this. So next what? What is over? Delta G over delta S over delta G. Next what? Obviously delta H. Next is delta, pick up this, delta H, delta H M ideal PT. What is this? Delta, next is delta H M ideal. Okay, is what? Tell me. You recall this? Delta G, delta G is H minus Ts. Recall this? Shall I show you here? G is H minus Ts. From this, delta G is delta H minus delta Ts from delta Ts. Delta Ts, if the temperature is constant here, okay, so delta H minus T delta S. Okay, this one. No, so what you will get here? Delta Gm ideal PT plus T delta Sm ideal PT. So you cannot afford to forget these basic relationships. Careful. So this is what, quickly substitute the value quickly, one line. RT first term, RT XLN XA, here, plus XBLN XB. Okay, and then next is T delta S is minus RT, delta Sm is here minus R, and T times means this one is 0. So this will be your what is this called, is 0. So I am writing separately, or delta H separate line ideal PT is 0. Call this equation 6. So three properties are found for ideal solutions. Okay, but what is the significance of this? Delta Hm ideal, constant pressure, constant temperature process. We recall Q is what? Under, recall, okay, I will ask you, under constant what? Under constant pressure. If it were under constant volume, what it is? Q is what? Delta U, internal energy change. Constant pressure, since here under constant pressure, and this still there is another constant. I will not write that because that is not relevant here. But what is that condition? That will be relevant in electrochemical cell. Is when there is no non-mechanical work, then only this is true. But since there is no question of non-mechanical, I am writing simply under constant pressure. Okay, Q is delta H under constant pressure. What is the delta H here? What delta H? In which form? Delta Hm ideal under pressure temperature is what value it is? 0. So what we get out of this? Q is 0, means no heat interaction. This means that, so we got very practical quantity and important thermodynamic as well as practical quantity heat interaction. How much heat will be interacted between system and surrounding. We place this. So this means that the heat interaction between system and between system and surrounding is 0, is 0. Means no heat interaction. This means what? That is neither, neither heat is admitted into the system from surrounding, nor heat is withdrawn from the system to the surrounding, So neither, no heat interaction. So you recall one thing. This is for ideal solution. Remember, this is ideal solution properties I am discussing. Ideal solution properties. 1, 2, so far 3. So no heat interaction or no enthalpy change, enthalpy of mixing. This I told you. Remember positive deviation and negative deviation in terms of enthalpy change. So for ideal for positive deviation, delta HMPT. For positive deviation, delta HMPT. For positive deviation, delta HMPT is what is this called? For delta HM is positive, and for negative deviation, this is negative. For obviously for ideal solution, it should be 0 and is 0 here. So very good. So next is what? Guess what is delta? I'll get this. I will remove this line. I don't want to. Maybe here it will be possible. Then I'll go up there. Next is what? Delta. Next property next. Delta Vm ideal constant pressure, constant temperature. Constant pressure, constant temperature. How will you get this? From free energy. Again, take help. dg is vdp minus sdt. So I use this. The basic equation, use this. Then you will get what you write. How do you get v dg dt under constant pressure? So write properly. Del is source. It is source relation. dg is vdp minus. So what is this? Del v. This is actually, you can write this. I wrote here a moment ago. Yes, I believe yes, I wrote there. Delta V dp here. I have removed this. I wrote a moment. Don't have to write. So you get follow this. So what is the V? dg del g del p. So del g here. Del g is what? Del g m ideal pt. Write this. Del g del p under what? Tell me. Under constant temperature, okay? Under constant, this drops, then del G del P is V. Under constant temperature, this time constant temperature and composition. So you again similarly, if you want to find this, carry out a number of experiments where pressure under constant pressure, constant temperature every time with a given composition, with a chosen composition, say 70%, 30%, etc. or 7 moles of A, 3 moles of B. But every time you keep changing pressure. So pressure 1 atmosphere, pressure 2 atmosphere, pressure 3 atmosphere, pressure 4 atmosphere. Not changing temperature. So temperature is say 500 Kelvin. So 500 Kelvin, or say a little bit practical. So 1000 Kelvin, 1000 Kelvin, 1000 Kelvin all the time. And composition that okay 70% A, 30% B, such things. Okay. So this is the practice. So this is the significance of this derivative, as I have already explained here. explained here. Okay, and okay, I have already explained. For this entropy, I have explained. Okay, so this is what, how much this will be. Tell me. Take a look. What is delta GM ideal? This is, you are okay, differentiating it with respect to pressure under constant temperature composition. Temperature and composition is constant. Temperature T is constant. Composition is constant. So all constant. So what is the derivative value? Delta P. So delta VM ideal. Okay. Another thing I tell you what, this is also should be what, should be. I should say. Shall I write here? Shall I write one line? Does it help you? Quickly. Del T. You write there. If it helps you, write here. What? Delta GM ideal. Write quickly. RT. RT, write this RT XA ln XA. Oh, RT, there is a bracket, so too many. Give a third bracket plus XB ln XP. Del T of this delta GM, del, oh, I am very sorry, del P under constant, tell me, temperature composition. What the result is? See, this is constant is, I am writing this side, in case, or is 0 right here? 0 is right here, I write once more here. Delta VM ideal is 0, and this should be equation 7. There is still another one. That is internal energy change. Achha, again, what is the name of this? Well, give the name at least here at least. What is the name? This is integral molar entropy of a mixing. Integral molar entropy of mixing. Integral, and this is integral molar free energy of mixing. This is what? Integral, tell me. Integral molar enthalpy, molar enthalpy of mixing. Similarly, it will be integral molar volume of mixing. So one thing I tell you here, what is the significance of this? Tell me one by one. Delta GM is, as you found later, is negative. Means, what does it mean? Means this is state 1 and state 2. Difference is negative, means this has lower free energy and initial state has a higher free energy. So the difference is product minus react is negative. This is the meaning of this. So suppose this together is 20 joule, then it will be less than 20, say 15 joule total free energy. Then you get 15 minus 20 is minus 5 is negative, that it is a negative quantity already. I have shown, and that is a spontaneous process. Delta SM ideal is likewise positive. I wrote somewhere. I wrote here. Positive means entropy of this together will be less than entropy of the product. What is this? This is very important. Enthalpy of mixing is 0. What is the meaning of this? Means this unmixed state has the same enthalpy as the mixed state. No change. If it is 10 joules together, then the solution is also 10 joules. What is this last one? Volume? No change in volume. So on addition, no change in volume. Suppose it is 5 cc, 5 cc or say 6 cc, 11 cc, and what is the volume here? 11 cc. No change in volume. This is the significance of this. Okay. So very good. Last one I will take up here. This space. Last one is internal energy. Similarly, so write this. This will, can I give a star here? Thank you. So what is this? Let us start. Delta UM similarly. Delta UM ideal. We are into the ideal solution we are discussing. Okay. Right from here. All ideal solution properties is what? pressure temperature you have to write. No way. Is right. What is the relation to get this? H is U plus PV. Clue. H is clue. What is this? Is delta HM ideal PT minus delta PV M ideal PT. Okay, like this. Okay, delta PV, or so simply delta HM delta PV under constant pressure, constant temperature. Okay. So what it is? Tell me. Is, let me write, delta HM ideal as you see, minus, since pressure is constant, P should be outside. P can be outside. Minus P delta V M ideal under constant pressure, constant temperature. Now substitute the value. What is this value? See here, 0. What is this value? See here, from 7, 0. What is this? 0 minus 0. Again another 0. This is called, this equation what? Or right here. Or delta UM, tidy up, PT is right here, is 0. Okay, is 0. Right here. Okay, no problem. Sorry. Is 0. So many zeros. This is 0, this is 0, this is 0. 3 zeros for ideal solution. Is 0 minus 0, 0. Call this equation what? This is 7. This will be 8. Okay, this segment is over. Good. Now I shall give you one thing. There is a plot of this. Now let me do, just start. These are all over. So the results are where? Results. Okay, results you remember. Some results I may retain. Some results I may retain. I'm writing you one by one. Delta. Achha. Let me remove this line. Good boy. Good boy. Just 3 results. I'll sketch them. I'll plot them against composition. 1, 2, 3. Free energy, entropy, and enthalpy. So I retain these values so that you can follow easily. Delta Gm saved. What is saved? Delta Gm, write this. Ideal PT is what value? You write this, you know very well. Is RT XA ln XA plus XP ln XP. Note here. Is a negative quantity. Is a negative quantity. You know very well, because ln XP is, as I've already explained, that's a spontaneous process also. So ln XP is a fraction, log of fraction is negative. So and next is another, you said delta Sm ideal PT. What is this? You tell me. Minus R XA ln XA plus XB ln XB. You see where? This one. This one is also, is you write it is a negative quantity, is a positive quantity. And the last is enthalpy. Enthalpy ideal is what? 0. Is it 0? 0. So once I have saved this, I remove all these lines and get some space for drawing diagrams, plot, schematic plot. So remove all this. So just these are saved. These three are saved. Okay. Now what is this next? Next, plot delta GM ID PT or short or अच्छा delta GM ID, delta SM ID PT and delta HM ID PT as a function of composition of the solution AB. So okay, one thing I still write this. XB say. Let us draw this. XB is moving from 0 to 1. The solution here, when XB is 0, it is pure A. When XB is 1, it is pure B. What you are plotting? Suppose this is your 0, 0. This is positive. This is negative. This is say 0.5. What is delta GM will be look like? Will look like sorry. Okay, this is the delta GM. This equation I have plotted. Symmetrical around 0.5, and there is a minima here, but I'll explain the significance of this minima. Actually, there is no significance of this minima, but I'll explain that. Delta GM ideal, okay? PT you can apply this, or simply delta GM ideal you may write. PT, or you can even remove this PT, okay? Short form, in short. This is delta GM ideal. And what is the this is delta SM ideal, as should be positive, as I have said. It's positive. This is negative. And what is the delta HM? Delta HM? I don't have to use. I use the same chalk, same color. This is what? 0. Delta HM idea. You in short you write, okay, constant pressure, constant temperature, you may drop, but you understand that it is a constant pressure, constant temperature. These three figures I have actually shown, okay, try to this. One thing here you have to note this, okay, this is this, okay. So, right here rather, instead of writing here all the time, constant pressure, constant temperature process. But this applies to everything. Okay, this is now. Now let us some discussion. Discussion about 0.5. There is a minima. I tell you some briefly. I tell you. These attain a minima. Mathematically, it can be shown by the calculus that it will be minima at 0.5. Delta Gm equation is here with you. Equation is here. It can be if you take the derivative and set it to 0, then you will get this minima at 0.5. This can very easily obtain. This equation is such that symmetrical, so very easy. And similarly, delta Sm also got a maximum at the corresponding point of 0.5. xB is 0.5. This is maxima. And delta Hm ideal is 0 through across the composition. So these are the observations. Now why it is minima? Now I am writing you, but I am telling you, you may think that minima is at means equilibrium. That is about chemical reaction. Chemical reaction, you move from reactant to product, there is equilibrium state in the middle. Other states are non-equilibrium. No, here all states are equilibrium. Equilibrium, all equilibrium. Starting from some A plus B, unmixed to mixed solution state. That is the final state is equilibrium state, you know. Unmixed state, mixed state is the equilibrium state. So each is equilibrium. There is no significance about that. This minima has no significance about that, that this is very particular. But there is another factor. Why it is minima? Rather, you consider why delta Sm is maximum. This you can understand through statistical thermodynamics. Statistical thermodynamics, if you remember, we consider 4A plus 4B, two container particles in a box. And when actually, you know, both sides is 4 for 2 at 2 atom of A, 2 particle of A and 2 particle of B on each compartment. We call this. Then there in that case, that was the maximum arrangement that gives microstates. So this happens when this will happen when this is actually equal number. This is actually this and entropy. If you recall this entropy is actually configurational entropy, not thermal. So statistical thermodynamics gives this, finds this value, same value, exactly same value, say exactly same value as classical now we are discussing, giving us. So no problem. So no problem. Okay. So this is happening. So shall I improve this one? A little bit improving this. This is little bit looks odd. Maxima, then it descends to this value, more or less, more better. Now this number of ways things are arranged. This is what? This gives you the number of microstate for a given macrostate. Number of microstate or number of complexons, or we said also degree of mixedness, probability, so many things. Is when achieved when this is equal number. Equal number of moles of A and equal numbers of moles of B. And when it is equal number, mole fraction is what? 0.5. 0.5 both. Okay. So that's why maxima is shown. Let us write these lines few important. Okay. Now at XA, XB is at XB, which is equal to XA when both are 0.5. XB is 1 minus XA. Remember, XA plus XB is 1. So XB is 1 minus XA. XB is 0.5. Delta Gm ideal. I am not giving constant pressure, constant temperature anymore. Unnecessary. You understand this? Is minimum. Minimum means all are negative values. And minimum, the most negative. Can I use this? Most negative at this point. This point, I mean. minimum. আচ্ছা, delta GM, and I have written this, and delta SM ideal is what? Maxima is positive. The positive, it is in the positive domain. This is negative domain. Is positive, is maximum, most positive. Okay, very good. These are the new things that we are discussing this today's class. These were not discussed last class. Okay. Also phase diagrams I will draw that will be new additions today. Okay. Next is what? Huh. And still and delta HM ideal. Tell me what you see. This is the delta HM. It is on the zero value. Is 0. Okay, happy. So the fact that delta GM ideal is minimum at xb is 0.5 is can be obtained from calculus by using what? Minima derivative is 0. For maximum also 0, but minima is 0 and second derivative is positive, etc. By using del d delta GM ID pressure temperature, you may add here also if necessary, is by dxp. By dxp is by setting this is 0. Then you will get this value dgm is 0, xb is 0.5 will become. Don't confuse. Don't confuse. Don't confuse this minima. This minima. This minimum with the minimum of with the minimum of G prime PT versus N curve for chemical reactions chemical reaction, say A plus 2B that we considered before, say A plus 2B is 3C. Discussed before. There the minimum is the equilibrium state and only one equilibrium state. Here all points are equilibrium. Minimum is mathematically coming from the equation. But there is entropy maximum has some insight and some implications that I will discuss. Let me complete this before. Okay, for the chemical reaction, minimum is equilibrium. Other points are non-equilibrium. All non-equilibrium. Here all equilibrium. For the what is this for? So before for the chemical reaction. Say A plus 2B is 3C. Oh, I have already discussed before. The minimum of the curve For a chemical reaction, for a better, the minimum of the curve identifies the equilibrium state. Identifies the equilibrium state. Equilibrium state. But in figure 1, call it figure 1. Call it figure 1. But in figure 1, but in figure 1, all points on delta GM, all points on delta GM ideal versus XB curve are equilibrium state of the all points on delta GM ideal versus XB means this curve. All points on this curve are equilibrium state of the corresponding solution. Are equilibrium states of the corresponding solution. This corresponding solution means for this composition, this is the equilibrium state. This is the free energy value delta GM, and this is the at equilibrium. Final state is equilibrium. Initial state, and after mixing, the mixed state is the final state for each, and the difference delta GM ideal product minus final state minus initial state is this, and this is all actually referred to the equilibrium state. So there is no special significance of the only mathematically. Mathematically it will come, okay. But now, however, there is a correspondence between correspondence between there is a correspondence between there is a correspondence between delta SM ideal being maximum and delta GM ideal being minimum. At XB is 0.5. Yeah, these 2 points, minimum, maximum. So this can be very easily shown also. Delta GM, just this may be the delta GM ideal is delta HM ideal minus T delta SM ideal. Now this is 0. This is 0 is minus T delta SM ideal. So when this is minimum, this maximum means this is minimum. This is minimum. Okay. So this is this, and its magnitude would be what? Its magnitude would be what? Suppose this composition you are considering. This composition. This composition. Say 0.2. What is this value and what is the relation between this value and this value at this composition? This will be, this is positive, this is negative, but this will be numerically T times the temperature T times this value, T times this value. Delta Sm is positive, so it is negative, but absolute value is T times. If temperature is 1000 Kelvin, the 1000 times greater this one numerically, but this is negative, that is positive. This is the meaning of this. A few more points, few more lines. You just give me some I shall write here. I think these already used this, but there is some implication star, double star. You don't need this. This here you have already used this, and you have plotted this equation. This is actually statistical discussion. There is some implication of just since this is okay, delta Sm ideal is. Okay. What shall I write here? Delta Sm ideal is what? Tell me. Minus R X A L. Oh ho 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 ho. I'm writing here below is minus R. Tell me. X A O ho bracket X A ln X A plus XP ln XP. So you can know this curve how this is the plot of this. This is, tell me, is minus RT, that is only RT XA ln XA plus XB ln XP. I have removed this here, and delta HM ideal is 0. Write this right here. Delta HM ideal is 0. I have given the equations also so that you can follow the plots. Okay, no problem. Now, there is some implication of delta Sm ideal being maximum at XB is 0.5. XA is also 0.5. Note this, XA is also 0.5. According to statistical thermodynamics, which we have already covered, according to statistical thermodynamics, this is what we are discussing. This is classical thermodynamics. According to statistical thermodynamics, this delta Sm ideal is all, you tell me what it is, what type of entropy change. This value is where I have written here, minus R XA ln XA plus XP ln XP. So this value is, according to statistical thermodynamics, what kind of entropy change? This is configurational entropy change, not thermal. Full configuration. This was derived when you are studying statistical thermodynamics, and we said that the same value will get in classical thermodynamics. So this is configurational entropy change means where actually how many ways number of atoms are A and B atoms are arranged in space, how many ways. And thermal entropy change is number of ways the energy can be shared among the particles. Okay, is all. This this SM ideal is all. This right is all configurational entropy change. Configurational entropy change. Change. Okay. This is very good. Configurational entropy change. No, write in bracket additionally, no thermal entropy change. And the configurational entropy change is dependent configurational entropy change is dependent on configurational entropy change is dependent on is dependent on number of microstates, number of microstates, number of microstates, number of microstates for a corresponding microstates or different name to this. Yes, another name is what? Complexions will be right here. Complexions. This is statistical term, technical term, complexions, or alternative. Another name is what? Mixed up degree of mixed upness, as gave this degree of mixed upness, or even probability. For a given macrostate, for a given macrostate. For a given macrostate, this number is maximum. This number I showed there with examples 4a and 4b. We showed this, and two separate box 4a and 4b. But the maximum number of arrangement was obtained when each box has 2a, 2b, 2a, 2b, and 2a, 2b, rather than 3, 1, 1, 3 or 4, 0, 0, 4. Recall this, okay? So this or this. So this is actually, if I remember well, this is actually. So this number is maximum. This number is maximum when equal number of moles of A and B leading to XA is 0.5, XB is 0.5 are considered. Are considered. Are considered. Okay. These days you have actually remember we are often speaking of high entropy alloys, and there actually the distribution is equal. So 25%, 25%, 25%, 25%. Here it is 50%, 50%, 0.5, 0.5. So these are the this is the rationale behind this, or this is the explanation behind that. Okay, but anyway, our purpose is solved. Why this is maximum? It is actually statistical origin. The explanation is obtained from statistical thermodynamics. Statistical distribution, okay, and maximum number of arrangements obtained. So this is maximum. If it is maximum, then delta G, which is minus T delta S, which is minus T delta S, will be minimum. Will be minimum. Okay, this is the reason. Also, mathematically, if you consider this equation and take this dxb of this, and set dxb of this, remember xb is 1 minus xa also, dxb of this function, of this expression, and set to 0, you will get xb is 0.5, and of course xa is also 0.5. Thank you very much. With this, we have completed today's lesson, and today actually I thought I would be able to start actually drawing some phase diagrams which is consistent with different solutions. Okay, ideal solutions, non-ideal solutions, in liquid solution state, in liquid phase and in solid phase, solid solution phase. But those diagrams actually I'll show next class. Next class I will show this, and also some additional discussion maybe. Then only I will be able to take up the excess functions, next thermodynamic functions. So thank you very much for your concentration, for your cooperation, for your patience, for your interest. Thank you very much. See you next class. Bye.